Hello everyone. In today's lecture, we will extend our study of the different trigonometric formulas to learn about the double angle, the power reducing, and the half angle formulas. Previously, we learned about the sum and difference formulas where we could find the sine, cosine, and the tangent ratios of the difference of two angles or the sum of two different angles. Here, we will start by talking about the double angle formula. Double angle suggests when angles are multiplied by two angles that are doubled. The power reducing formula when trigonometric functions are raised to an exponent, how we can reduce it to a lower power. And then the half angle formulas is where angles are divided by 2. These are the topics that will be covered in this lecture. We'll start with the double angle formulas and their applications. Then we'll go on to the power reducing formulas and how to apply them. And finally, the half angle formulas and their uses. We will begin with the double angle formulas. To start with, the sine of 2 times theta is equal to 2 times sine theta times cos theta. Cos of 2 times theta equals cos squared theta minus sine squared theta, and tan of 2 times theta equals 2 times tan of theta divided by 1 minus tan squared theta. Now, each of these identities or formulas can be verified using the sum and difference formulas that we learned previously. I will verify the first one for you, the sine of 2 times theta identity, and I'll leave it up to you to verify the other two using the same process and the same logic. So 2 times theta can be written as the sum of two thetas, correct? We can rewrite 2 times theta as theta plus theta, the sum of two angles but of the same measure. We can therefore rewrite this sine of 2 times theta as sine of theta plus theta, the sum of two angles of the same measure for the sine function. What was the formula for the sum of two angles for the sine function? Let me write that down here. It was sine theta times cos theta. The two angles are the same. Alpha and beta are the same here. So sine of theta times cos of theta plus cos of theta times sine of theta. Now, because both alpha and beta in this case have the same measure of theta, we can write this as sine of theta times cos of theta. Now, cos of theta times sine of theta is the same as sine of theta times cos of theta, correct? We can just switch the factors and write it as sine of theta times cos of theta, which is the same as the first term. So we can combine them and rewrite it as 2 times sine theta times cos of theta. So now we have verified the sine of 2 times theta formula using the sum formula for the sine function. Here's the first example of using the double angle formula to find an exact value. The question is, if sine of theta equals 4 over 5 and theta lies in quadrant 2, find the exact value of sine of 2 times theta. So they've given us the sine ratio of a certain angle. They haven't given us the angle measure, but they just name it as theta. But we know the ratio for it, and we are also told that it's a quadrant 2 angle. We need to find sine of 2 times theta. Let's recall what the formula for sine of 2 times theta is. So sine of 2 theta equals 2 times sine theta times cos theta. So in this formula, we know what value to plug in for sine of theta, but we do not know what to plug in for cos theta yet. For that, we have to find the third side of the right angle in the second quadrant. Right? We have to make use again of the Pythagorean formula. So here we have a picture of an angle in the second quadrant where sine of theta equals 4/5. So that's y divided by r, correct? Y is the value of 4 and r has a value of 5. Therefore, in this picture, the right triangle has the hypotenuse length r as 5 and the vertical length as 4. We need to find the measure of x, and that's going to be a negative value because this is on the negative x-axis. Using the Pythagorean formula, we come up with x squared plus y squared equals r squared. Plug in the values for y and r, and we get x squared plus 4 squared equals 5 squared. We need to solve for x here. So x squared plus 4 squared is 16, 5 squared is 25, which gives us x squared equals 9, and therefore x equals negative 3. So we choose negative 3 again because this is a second quadrant angle. And once we have found the value of x, we will know what cos of theta will be. Cos is defined by the formula x divided by r, so it's going to be minus 3 divided by 5, and that's what is shown here. And now that we know what sine of theta is, we know what cos of theta is, we plug in those values into the formula. So 2 times 4/5 for sine of theta, and cos of theta is minus 3/5. Plug in that ratio for cos of theta and complete the operation. So that's minus 24 divided by 25, and that's the final answer. The second example related to the same problem is asking us to find the exact value of cos of 2 times theta. Therefore, again, sine of theta is still a second quadrant angle and its ratio is 4/5. We need to find cos of 2 times theta. Now, in the previous example, we already found the values of sine of theta as well as cos of theta. This time, all we need to do is pick the right formula, plug in the values appropriately, and perform the calculation. So here we have the picture of the same angle, the same side values. The vertical side has a value of 4, the radius has a value of 5. We know what x is, it's negative 3. Therefore, we had put together sine of theta being 4/5, cos of theta equals negative 3/5. Let's pull up the formula for cos of 2 times theta, and that's cos squared theta minus sine squared theta. Therefore, we are going to plug in minus 3/5 for cos of theta and square it, then a minus sign followed by the sine ratio is 4/5. We need to square it, and when we perform the operation, we end up with a ratio of minus 7/25, right? So that's the answer to exact value of cos of 2 times theta using the double angle formula. The third part of the question asks us to find tan of 2 times theta for the same angle measure in the second quadrant, which has a sine ratio of 4/5. Previously, we already found the values of x, y, and r. We know the value of sine theta 4/5. We know the value of cos theta is negative 3/5. We just need to put the ratio for tan of theta. Tan has a formula of y divided by x. Y equals 4 and x equals negative 3. So the tan ratio for theta is going to be negative 4/3. Now we have to bring up our formula for tan of 2 times theta and plug in the values correctly and perform the calculation to get our answer. So tan of 2 times theta equals 2 times tan of theta divided by 1 minus tan squared theta. So plug in the values, there's 2, and then tan of theta is negative 4/3. Negative 4 divided by 3 divided by 1 minus 4/3 whole squared. The minus here is also squared. Therefore, when we perform the calculation, 2 times negative 4/3 is negative 8/3, and then the denominator calculates to 1 minus 16/9. When you square a negative, you get a positive. So negative 4/3 squared is 16/9, and then we have the negative sign outside the brackets. And once we complete the calculation, we get negative 8 over 3 divided by negative 7 over 9 for a value of 24 divided by 7. So there's negative in the numerator, there's negative in the denominator. What we are doing here is, remember, dividing fractions. So we change the division to a multiplication and we flip the numerator and denominator of the denominator, and we end up with a value which is positive 24 by 7, and that is what tan of 2 times theta will be. Now at this point I want to remind you that previously, if you look back, sine of 2 times theta was a negative value. Cos of 2 times theta was also a negative value, but tan of 2 times theta happens to be a positive ratio. So even though the question said theta lies in quadrant 2, 2 times theta, when you multiply theta by 2, it is no longer a quadrant 2 angle, it becomes a quadrant 3 angle. Remember the ASTC rule. By the ASTC rule, in the third quadrant, sine and cos are both negative and tan would be positive. So once you multiplied your theta by 2, once you doubled it, it's no longer a quadrant 2 angle, it is a quadrant 3 angle. How did we know that? By looking at the sign of the different ratios of 2 times theta. Sine of 2 times theta, cos of 2 times theta, and tan of 2 times theta, right? So far we have learned only one form of the double angle formula for cosine, which was cos squared theta minus sine squared theta. However, there are two other forms which are derived from the first form, which is cos of 2 times theta equals 2 times cos squared theta minus 1 and 1 minus 2 times sine squared theta. I will show how the second form has been derived from the first form using the Pythagorean identity that we had learnt previously. If you recall, the Pythagorean identity said sine squared theta plus cos squared theta was equal to 1. Correct? That's the Pythagorean identity. However, we can rewrite sine squared theta equals, we can have the sine squared theta by itself on the left hand side and write it as sine squared theta equals 1 minus cos squared theta. We had learnt this form also previously and even applied it to solve some problems. So now that we know that sine squared theta equals 1 minus cos squared theta, we can plug in this expression 1 minus cos squared theta into the sine squared theta term for the first form of the double angle identity for cosine, correct? So I'm going to rewrite here this entire formula. Cos of 2 times theta equals cos squared theta minus sine squared theta. In the next step, I will keep cos squared theta as is and the minus sign following that, and I'll replace sine squared theta with this expression 1 minus cos squared theta. We will get cos squared theta minus 1. When you distribute the minus to the terms inside the brackets, minus minus will become a plus. So we are going to write it as plus cos squared theta, and now we will combine the two cos squared thetas and write it as 2 times cos squared theta minus 1, and that is exactly what we have for the second form of the equation. So I will leave it up to you to work out the third form, how that can be derived using one of these forms here. Alright, we will now work on an example of verifying an identity using not only the double angle identities but also the sum and difference formulas that we had learnt previously. The question is, verify the identity which is sine of 3 times theta equals 3 times sine of theta minus 4 times sine cube theta. Now, unlike in previous time, this time we will not work with the more complicated side of the identity. Instead, we will work with sine of 3 times theta because this looks more relevant on which the double angle identity be applied. So, in the first step, we will split up 3 times theta and write it as the sum of two angles. Therefore, sine of 3 times theta is written here as sine of, within brackets, 2 times theta plus theta. This is where we will apply the sum formula for the sine function. So that's what we are going to do in the next step. Here, alpha has a value of 2 times theta, beta has a value of theta, and by the sum formula for the sine function, it's written as sine of 2 times theta times cos of theta plus cos of 2 times theta times sine of theta. Correct? So in the next step, we will be plugging in the formula for sine of 2 times theta and cos of 2 times theta and rewrite this expression. So we have 2 times sine of theta times cos of theta. That is the formula for sine of 2 times theta, and then of course we have the cos of theta and then the plus sign followed by the formula for cos of 2 times theta is 1 minus 2 times sine squared theta. Recall that there are 3 forms of the double angle formula for cosines, correct? So this is one of the 3 formulas, 1 minus 2 times sine squared theta, and so this entire expression 1 minus 2 times sine squared theta replaces cos of 2 times theta, and then we have the sine of theta outside the brackets. Next step will be to distribute and combine terms. 2 times sine of theta, now cos of theta times cos of theta is cos squared theta, plus now sine of theta times 1 is sine of theta, minus 2 times sine squared theta times sine of theta is 2 times sine cube theta. So that's how we ended up with the expression in this step. Let's pull up the next step, which is 2 times sine of theta. What they've done here is they've replaced cos squared theta by 1 minus sine squared theta, and that comes from the Pythagorean theorem that we had learned way back at the start. So we have 2 times sine of theta times 1 minus sine squared theta. So cos squared theta has been replaced by this entire expression, and then we have the plus sine of theta, which is here, and then minus 2 times sine cube theta. Right, so this is going to continue in the next slide for the next few steps. Here we've brought over the expression from the last step of the previous slide, which was 2 times sine of theta times 1 minus sine squared theta plus sine of theta minus 2 times sine cube theta. So we're going to distribute the 2 times sine of theta to the terms in the brackets 1 and negative sine squared theta, and we will get 2 times sine of theta. 2 times sine of theta times 1 is 2 times sine of theta minus 2 times sine of theta times sine squared theta is 2 times sine cube theta, and then plus sine of theta minus 2 times sine cube theta. The last step will be to combine the like terms. Now 2 times sine of theta will be added to 1 times sine of theta for 3 times sine of theta, and then the other one is 2 sine cube theta will be combined with 2 sine cube theta. So it's negative 2 and negative 2 when combined will give us 3 times sine of theta minus 4 times sine cube theta. Now we'll study the next set of formulas known as the power reducing formulas. As we see over here in the list of formulas given to us, all the trigonometric functions are squared. So sine squared theta, cos squared theta, and tan squared theta. However, on the other side of the equation, we do not see any power. What that means is they have reduced the exponent and rewritten it as an expression without any exponents. So we have sine squared theta equals 1 minus 2 times cos of theta divided by 2. Then we have cos squared theta equals 1 plus cos of 2 times theta divided by 2, and then finally tan squared theta equals 1 minus cos of 2 times theta divided by 1 plus cos of 2 times theta. So we will go into seeing how we apply these power reducing formulas. We'll now work on an example of reducing the power of a trigonometric function. The question says write an equivalent expression for sine raised to the power 4 of x that does not contain powers of trigonometric functions greater than 1. The exercise here is to work with sine raised to the power 4 of x and come up with an equivalent expression which will not have any powers that are greater than 1. Right? So let's go through the process here. We start with sine raised to the power 4 of x and rewrite it as sine squared x whole squared. So we have applied the power rule of exponents that we were taught in algebra, and we rewrote sine raised to the power 4 of x as sine squared x whole squared form. And then the next step is to replace sine squared x using the power reducing formula, which is 1 minus cos of 2x divided by 2. In the next step, we will square this entire expression and we will get 1 minus 2 times cos of 2x plus cos squared 2x. How did we come up with this expression? Recall the formula we had learned way back in algebra, which was a minus b whole squared. A minus b whole squared. To expand that, we were given a formula which is a squared minus 2ab plus b squared. So here a has a value of 1, b has a value of cos of 2x. So applying this formula, we got 1, a squared, 1 squared is 1, and then the minus sign, 2 times 1 times cos of 2x, 2 times ab. So 2 times 1 times cos of 2x is the middle term here, and then the plus sign followed by cos squared 2x, which is b squared. B is cos of 2x. When we square that, we get cos squared 2x. Now the square has also to be applied to the denominator. So 2 squared is a 4, and that's how they came up with 4. And now we distribute the common denominator of 4 to all the terms and separate them. So we have 1/4 for the first term minus 2 times cos of 2x divided by 4. This 2 and 4 divide, so we have 1/2. That's why 1/2. This 2 and this 4, if it divides, we will end up with 1/2. And then 1/2 cos of 2x plus 1/4, again, cos squared 2x divided by 4 can be written as 1/4 times cos squared of 2x. And then we have 1/4. We are working further down because now we will replace cos squared of 2x using the power reducing formula for cos squared of theta. Right? So 1/4 stays the same. The first term stays the same. Minus 1/2 times cos of 2x stays the same. Nothing to substitute here. But for the last term, plus 1/4, we will replace cos squared 2x with the formula for the power reducing identity for cosines. So cos squared of 2x is 1 plus cos of 2 times 2x. Correct? This is theta over here. This represents our theta. So this is theta. So the formula was 1 plus cos of 2 times theta divided by 2. We replace the theta with 2x, and that's how we came up with this expression. Now this will go on to the next slide, but in the next slide you will see that we will multiply everything out by 1/4. Let's continue to the next slide. Here's the expression that we brought over from the previous slide, which was 1/4 minus half times cos of 2x plus 1/4, and then within brackets 1 plus cos of 2 times 2x divided by 2. Now, as you will notice that we've already managed to reduce the power of the trigonometric function we had started with, which was sine raised to the power 4 of x. The x variables in this expression are all raised to the power 1. So we have reduced the power of the trigonometric function from an exponent of 4 to an exponent of 1 at this point. The rest of the steps will involve simplifying this and reducing it and writing it in its lowest terms. So let's pull up the next steps. There's nothing to reduce in the first term of this expression, 1/4. Then we have half times cos of 2x in the second term, which is already in its lowest form, in its reduced form. It's the third term that needs further work, that needs further simplification. So we will work on the third term in the next step. What we do is, in the third term, we factor out the 2 from within the brackets and multiply the 4 with it, and we end up with 1/8 times 1 plus cos of 4x. So in the numerator, we have 2 times 2x gives us the 4x. In the next step, we distribute the 1/8 to the terms within the brackets, and we end up with 1/8 plus 1/8 times cos of 4x. So that's how we end up with the expression for the third and the fourth term. In the last term, we will combine 1/4 and 1/8. We will add 1/8 to 1/4, and that will complete our answer here. So let's pull up that. So 1/4 plus 1/8 gives us 3/8, and then the second term stays as is, minus half times cos of 2x, and the third term is 1/8 times cos of 4x. We will look at the third set of formulas known as the half angle formulas. That happens when alpha, the angle measure, is divided by 2, is halved. Let's look at the formulas for the sine of alpha by 2. That's equal to plus minus square root over 1 minus cos of alpha divided by 2. Cos of alpha divided by 2 equals plus minus square root over 1 plus cos of alpha divided by 2. Tan of alpha divided by 2 equals plus minus square root over 1 minus cos of alpha divided by 1 plus cos of alpha. Now, let me point out that the plus minus before the radicals do not mean that there will be two values, one positive and one negative, for the answer. Depending on which quadrant alpha by 2 will lie, we will have to choose the appropriate sign for that particular function and append it to the ratio. So that's what the plus and minus are here for. All right, so let's go through an example in the next slide. Let's work on an example for using the half angle formula to find an exact value. The question says use cos of 210 degrees equals negative square root over 3 by 2 to find the exact value of cos of 105 degrees. So they have given us the cosine ratio of the angle 210 degrees, and they want us to find the exact value, the exact cosine ratio for 105 degree angle. So 105 degree angle is half of 210 degrees. So in other words, we have to find the cos of 210 degrees divided by 2, which is 105 degrees. So given that information, let's go through the steps. First of all, cos of 105 degrees equals cos of 210 divided by 2. We already said that previously. In the next step, we have to use the formula for cos of alpha by 2, which is plus minus square root over 1 plus cos of alpha divided by 2. 210 degrees is an angle in the third quadrant. It has a negative cosine ratio. However, the angle which is half of 210 degrees, the 105-degree angle, is an angle in the second quadrant. The quadrant has changed after we divided 210 degrees by 2. Therefore, you have to remember the sign for the cosine ratio will be a negative because cos is negative in the second quadrant. Therefore, in the next step, we just use the negative sign in the formula and plug in the values and rewrite the expression as negative square root over 1 plus cos of 210 degrees divided by 2. Now we have to complete the calculation of this to come up with our answer, which we'll do in the next slide. In this step of the exercise, we will be multiplying both the numerator expression as well as the value in the denominator by 2. Now the expression in the numerator has two terms in it, 1 plus negative square root over 3 by 2. We have to distribute the 2 to both the terms and perform the multiplication. And in the denominator, we just have a value, so 2 will get multiplied by 2 for a value of 4. Now, there is a twofold purpose behind this, because first of all, this step will not only take care of the rationalization of the denominator. Somewhere down the line we would end up with a radical in the denominator and we would need to rationalize that. So this step will take care of that, and also it will remove the denominator from the numerator. 2 and 2 will divide, and it will remove the denominator from the numerator expression. Right? So what we'll end up with in the next step is the negative sign outside the radicals, and then the square root over 2 times 1 gives us a 2 in the numerator, the first term, minus, now plus times minus is a minus, that's how we got this minus, and then square root over 3 by 2, this 2 and 2 divides, so we end up with square root over 3 as the second term in the numerator. In the denominator we have 2 times 2, which is a 4. Now, the last step is to distribute the radical sign, the overall radical sign, to both the numerator and denominator to simplify further and get it to its lowest level. So we will end up with negative, and then in the numerator we will have 2 minus square root over 3. In the denominator we will have square root over 4. So I distributed the radical sign to both the numerator and denominator. Square root over 4 is a 2, therefore the final answer is negative square root over 2 minus square root over 3 in the numerator divided by 2. Finally, let's look at two other forms of the tangent functions for half angles. Tan of alpha by 2 equals 1 minus cos of alpha divided by sine of alpha, and the other form is sine of alpha divided by 1 plus cos of alpha. They are all equivalent expressions for tan of alpha by 2.